Standard 9 is about the function concept. One of the cool things about math is that it can be used to predict all sorts of situations. You can use it to predict things in nature, you can use it to predict things in business, you can use it to predict the results of science experiments. And if you can find a way to use math to predict what's going to happen, you've created a function. And functions are very useful because it's good to be able to use math to predict things. So here's a situation. If an object is moving at a constant rate, the distance it follows after a certain time can be found with this equation. Distance equals rate times time. You've probably heard of that equation before. So before we look at this equation and decide if it can be used to predict or not, we're going to need to know some graphing vocabulary because we're going to graph a picture of this equation to help us figure out what's going on. So here's a grid that's often used to make graphs. The grid is called a Cartesian plane. And on the grid, you usually find a set of axes. So there's one, there's the other. Usually you put arrows on the end to show that they go forever in all directions. So the horizontal axis is typically called the x-axis, although in this situation we're going to use time. And the vertical axis is typically called the y-axis, although for this example we're about to use, that's going to be distance. Make that x look more like an x. All right, so on the Cartesian plane, you typically put a point. So here's a point. And this point can now be described by two coordinates. It's going to have an x coordinate and a y coordinate. So to get to x here, I started at the center. I went over 1. So the x coordinate is 1. The y coordinate, I went up 2 to get to that one, so the y-coordinate is 2. And you typically write those in an ordered pair because the x-coordinate comes first and the y-coordinate comes second. A special point on the Cartesian plane is the origin. That's the point right there in the center. So that's the origin. And it has an x-coordinate of 0 and a y-coordinate of 0. You can see the axes divide the Cartesian plane into 4 different parts. These 4 parts are called quadrants, and they're usually labeled with Roman numerals. So this quadrant here is called quadrant 1. This is quadrant 2, quadrant 3, and this is quadrant 4. In quadrant 1, the x and y coordinates are both positive. In quadrant 2, you've moved over to the left side of the origin, so the x's will now be negative. In quadrant 3, you're to the left of the origin and you're also below the origin, so that makes x and y both negative. And in quadrant 4, you're still down below the origin, but you've moved back over to the right, so x is positive and y is negative. So now let's look at this distance and time equation again. Distance equals rate times time. So let's say you're walking casually down the street and the rate that you're moving at is 2 miles per hour. So let's draw some axes on here. Put the arrows on the end. So this axis here is going to be time, and this axis here is going to be distance. So after 1 hour, the distance you've gone is going to be 2 miles per hour times 1 hour, or 2 miles. So 1 hour for time, 2 miles for distance. That's that point right there. After 2 hours, you'll have gone 2 times 2, or 4 miles. And after 3 hours, you've gone 6 miles. At the very beginning, when the time was 0, you hadn't gone anywhere at all, so let's put that point on there. And then we'll connect all those. And I'll put a little arrow at the end to show that time could keep on going and the distance would keep on going. So let's look at this equation. Can I use it to predict if I go for 1 hour, I'm always going to go 2 miles. If I go for half an hour, I've gone 1 mile. There's no question at all. After half an hour, I haven't gone 3 miles or 6 miles. It's pretty clear that you can use this equation to predict. If you give it a time, it's going to tell you a distance. There's going to be no questions there. So this thing is a function. Each value for time gives only one value for distance, so the equation can be used to predict. That means it's a function. Let's talk about a little more vocabulary here. The domain is all of the values you put into the equation. So for this example, time is what I was putting in. And the range is all of the values you get out of the equation. In this example, it was distance, but very often it's y. So what were the domain? All of the values I put into this equation, it started at 0, because that's when the time started, and it kept going higher and higher. Negative time doesn't usually make a lot of sense, so all of the numbers I'm going to put into this equation would be positive. So for this example, the domain is all positive numbers. Now, last chapter we learned interval notation to describe a range of numbers. I'm going to use that. So I start at 0. I use a square bracket because I did include 0. And the numbers can go all the way up to infinity. It would be a long walk, but you could keep walking forever in theory. The range would be all of the values I get out of the equation. So looking at this equation, the distance can be 0 or it can keep going on forever and ever. So the range for this equation is going to be the same. It's going to start at 0, it's going to include 0, and it's going to go until infinity. To find the domain and range of any function, it's usually best to graph it first so you can get a picture of what's going on, and then draw your conclusions. Let's look at a picture of another equation. I'm not going to show you the equation, we'll just look at the picture. So I'm going to start with a point here at x equals 3. I'm going to put another point up here at y equals 3. Let's go back here to -3, down to -3. Connect all those. It's kind of a funny looking equation. You'll learn more about that equation in a more complicated math class. But let's just decide if that equation would be a function or not. So let's pick a value for x. Let's say x is 1. So if x is 1, what are my choices for y? Well, y could be up here, or y could also be down here. So for this one value of x, I have two different values of y, a positive one and a negative one. If you go back and look at the definition for a function, it tells you you can predict with it. If I give you a value of x, you know for sure what y is. But for this value of x, there's two different possible values of y. So this equation is not a function. And if an equation is not a function, it's a relation. Another way to show if a picture of an equation is a function or not is by doing a vertical line test. When you do a vertical line test, you imagine a vertical line traveling across the whole picture from left to right. So here's a vertical line, and I imagine it moving across, moving. If the vertical line finds any place in the graph where it touches more than one point, then you do not have a function. So this vertical line, pretty much every place going across the graph, it's going to touch the circle at the top and the bottom. So this picture fails the vertical line test. If you go back to the equation we had in the last example, I'm just going to draw a quick sketch of it here. So, quick x and y grid. The line looked something like this. So if you were to put a vertical line across this equation, here's a whole bunch of vertical lines, Each one of those vertical lines only touches the line once. So this equation will pass the vertical line test, and as we saw last time, it was a function. Once an equation has been shown to be a function, it can be rewritten in function notation. So here's an equation, we're going to draw a picture of it, decide if it's a function or not, and then we'll put it in function notation if it is a function. So to make a picture, I'm going to put in some values for x and see what I get for y. If x is 0, 2 times 0 is 0, so there's y. If x is 1, 2 times 1 is 2. If x is 2, 2 times 2 is 4, etc. How about negatives? If x is negative 1, 2 times negative 1 is negative 2. 2 times negative 2 is negative 4. So I'm going to draw that graph. And now I'm going to decide if it's a function or not. I'm going to use the vertical line test. So I'm going to imagine a vertical line going from left to right. It only touches the line at one point as it goes across the whole line. So this is a function. Now that I know that, I'm going to change to function notation. In place of y, I'm going to put f of x equals 2x. That looks kind of like f times x, but that's not what that means. This means that it's a function of x, and it's read f of x. Now let's do some calculating with our function notation. So f of x equals 2x. I'm going to find the value of the function when x equals 1 and when x equals negative 3. So f of 1. Wherever I see an x in the function, I'm going to put a 1 equals 2 times 1. And 2 times 1 is 2. So f of 1 equals 2. It's exactly what we were doing when we made the graph. If x equals 1, we found that y was 2. But now we just use this different notation that means we've shown it to be a function. Let's find the value of the function at negative 3. So in place of x, I'm going to put negative 3. And 2 times negative 3 is negative 6. Let's look at some more complicated functions. So for each one of these functions, I'm going to find the value of f of 2 and f of negative 3. So for this first function, f of 2 equals 4 times 2 minus 3 equals 8 minus 3 equals 5. It's just like calculating the value for x equals any number that you've always done. You just have this new notation to show that this equation is a function. Let's also find the function at negative 3. So that's going to be 4. I'm going to use parentheses this time so it's real obvious how the negative is going with the 3. Minus 3. So 4 times negative 3 is negative 12 minus 3, which is negative 15. Now we'll do a little bit more complicated function. So for this function f of 2, same deal. Wherever I see an x, I put in a 2. 2 squared minus 5 times 2 plus 2. So order of operations tells me I do the exponent first. Then I'm going to do the multiplying. For addition and subtraction, you just go across left to right. So 4 minus 10 is negative 6. And negative 6 plus 2 is negative 4. To find the value of the function at negative 3, that's going to be negative 3. I'll use parentheses to make it real obvious where the negative goes. Minus 5 times negative 3 plus 2. So negative 3 squared is positive 9, and negative times negative is a positive. Minus 5 times negative 3 is negative 15 plus 2. Subtracting a negative is the same as adding a positive. 9 plus 15 is 24 plus 2. So f of negative 3 is 26. Sometimes we're just going to look at a set of points and see if it determines a function or not, and not look at a whole equation. So here's a set of points. I'm going to draw a picture of them on the Cartesian plane, and once again I'll use that picture to help me decide if these points represent a function or not. So 3, 2 is right here. Negative 1, 4 is up there. 4, 3 is right there. 3, 0 is right here. And negative 3, 6. 1, 2, 3, 4, 5, 6 is right there. So looking at these points, let's see. If x is negative 3, y is 6, all good. If x is negative 1, y is 4, all good. When I get here to x equals 3, I have two different points right on top of each other. I have 3, 0 and 3, 2. So if x is 3, I don't know for sure what y equals. I can also use the vertical line test from the last slides. So if I draw a line right here at x equals 3, that line goes through 2 points. So this set of points does not make a function. If x is 3, I don't know for sure what y is. It could be either 0 or 2. So this is not a function. It is a relation. So if a set of points is given, you look at each x and see if it has a different y with it. If each x does have a unique value for y, the relation is a function. If not, like in the example we just saw, it's a relation. Let's look at another set of points. So 8, 2, 0, negative 2, and 6, 7. I'm going to look at each x and see if it has a different y with it. An x of 8 is a y of 2. I don't see any other x's of 8, so far so good. The next one, x is 0, y is negative 2, no other zeros for x. 6, 7, no other 6's for x. So each one of these x's, there's not going to be any duplications. Each x goes with only one y. So that's going to make this set of points a function. Now that it's a function, I can go through and look for the domain and the range the same way I did for the graphed ones a few slides back. So the domain is going to be all of the x values, and it's easier if it's just a set of points. You just make a list of the values. So the domain is going to be 8, 0, and 6. And the range is a list of all the y's. It's 2, negative 2, and 7.